Everyone, good morning. It's an honor to have the opportunity to address. The purpose of this presentation is to introduce a novel diagnosis method of depression based on EEG and convolutional neural networks. I will divide my presentation into 4 parts. The first part deals with introduction. The second part relates to model. The third part concerns experiment, and the last part discussed conclusion. Firstly, I would like to introduce the background of our research. According to the statistics of the World Health Organization, nearly 350 million people suffer from depression around the world, and it is estimated that more than 95 million people in China are suffering from depression. Depression is a very harmful disease with high self-mutilation rate, high suicide rate, and high recurrence rate. In past, doctors used scales to diagnose depression, such as SDIs. But this method usually takes 10 to 20 minutes to answer questions because of the strong subjectivity. The diagnosis result is not accurate enough. In recent years, more and more researchers identify depression based on the EEG signals. EEG as a physiological index is objective enough. Secondly, I would like to introduce the model in our paper. There are many methods to identify depression based on EEG. Some researchers use support vector machine or other machine learning methods to classify EEG signals. But these methods need to extract features manually. Deep network work such as LSTM CNN can solve this problem. It can automatically extract features. In the past studies, LSTM and CNN only considered the time domain or frequency domain characteristics of EEG, but EEG also includes spatial information. Therefore, this study proposed a new input form by combining the frequency of EEG with the electrode position. In order to classify EEG in the form of images, we propose a two-dimensional CNN model. The proposed 2D CNN structure is shown in the figure. It consists of 4 convolution layers, 2 max pooling layers, 1 flattened layer, and 2 dense layers. Now we move to the part of experiment. The experiment data of this paper are provided by the psychiatric department in 3 A-grade hospital in China. The subjects include 16 patients with depression and 16 healthy people. In order to meet the sample size requirements of deep learning, the signal is clipped into a segment of 100 sample points. In addition, there is 50% overlap rate between adjacent segments. So there are 15,053 segments of 32 subjects in total. The data need to be pre-processed before input to the model, including fast ICA to remove the electroencephalogram and FFT to extract the frequency band. Azimuth equidistant projection is used to project the position of the electrodes in 3-dimensional space onto a 2-dimensional plane. We extract the theta, alpha, and the beta bands of EEG signals respectively and calculate their power. Repeat the process for theta, alpha, and beta bands to generate 3 maps, which are combined to form an image with 3 color channels. The process of EEG signals classification is shown in the figure. The size is of convolution kernel is 3 times 3, which is commonly used in most networks. The number of convolution kernels is 32 and 64, according to the size of training data. The size of max pooling is 2 times 2. The size of flatten is 1024. The size of dense are 10 and 2. The size change of the feature map is shown in the figure. This model structure keeps a balance between training time and accuracy. When training the model, the dataset is divided into training set, validation set, and test set, each accounting for 70%, 10%, and 20%. For the choice of hyperparameter, we have done some comparative experiments. Among the results, the best set of hyperparameter is as follows. Dropout is set to 0.25, batch size is set to 100, epoch is set to 100. In order to measure the quality of the model and the classification results, we chose the accuracy, precision, recall, F1 score, and loss as the evaluation criteria. The classification results are shown in the table. We can see that among all the evaluation criteria, 2D-CNN is the best model. Now we come to the last part, conclusion. In this study, we propose a novel diagnosis method of depression based on EEG. It is more accurate and objective than the scale. Meanwhile, we propose a 2D convolutional network for classification. It has better classification results than SVM, LSTM, 1D-CNN. The future direction of diagnosis of depression can be considered from the following 3 aspects. Can we find the best parameter setting quickly and accurately? Can we improve the training speed of the model and get the diagnosis result quickly? Can we classify the degree of depression into 4 categories, such as normal, mild, moderate, and severe? That's the end of my presentation. Thank you for listening.